Okay, so how's everybody doing? Good? Okay. So I'm Tommy Wen Chen. I'm an undergrad at San Jose State University. This work was done in collaboration with Kelsey Bates of U Michigan under the supervision of Dr. Chris Mawat at San Jose State University. And this project was funded by the NSF. I'll be talking about modeling hidden silicon vacancy centers in Diamond. Among its various applications, SIV centers represent a strong candidate for the quantum network. In comparison to the more well-studied NV centers, SIV centers exhibit a really good and suitable optical properties for this particular application. For example, due to its inversion symmetry, SIV centers have a really sharp and narrow zero photon line. However, the spin coherence time of SIV centers is significantly lower than NV centers. Thus, no one system is perfect. In addition to SIV and NV centers, there are a whole variety of different color centers out there, a lot of whose composition are not well understood. This is good because for experimentalists, this opens up a whole lot of venues for exploration. One of the ways experimentalists shed light on these color centers is through spectroscopy. In our case, we use a nonlinear optical spectroscopy technique called multidimensional coherent spectroscopy, MDCS for short. In MDCS, we will send in multiple pulses of light with varying time delays. In our case, we send it to a silicon-infused diamond sample. This specific MDCS technique that we're using is called photoluminescence, where we will send in 4 excitation pulses and detect via radiative decay. If we go ahead and Fourier transform with respect to 2 of our time delays, for instance, the t and tau delays, we can produce a 2D spectrum. We can think of MDCS as a 2D NMR technique, an optical version of a 2D NMR. The 2D spectrum provides a whole lot more information compared to the 1D spectrum. For example, the diagonal width represents a measure of the inhomogeneity of our system. The off-diagonal represents the decoherence time. In addition to photoluminescence detection, we were also able to perform a different MDCS technique called heterodyne detection, where we would send in 3 excitation pulses and detect via radiative and non-radiative decay. To much of our surprise, we get a significantly different spectrum. Namely, we see a whole bunch more SIV centers that are visible under heterodyne detection, but are hidden under photoluminescence. This raises the big question of why are these 2 spectra so different, despite being from the same diamond sample? The paper reference below provides a number of compelling arguments that strain SIV centers play a significant role in this difference. In my specific project, I'm working on some follow-up work to this research in that I'm developing theoretical models of our system that can hopefully explain this difference. I start off by creating a simulation of the heterodyne detection. I start simple with a 2-state system separated by a 0 photon line. And I solve for the MDCS signal, which is proportional to a subset of the phase match 3rd order density matrix perturbation third order density matrix contributions. I employ density matrix perturbation theory, where I can solve for the n order correction in terms of the n-1 correction term. Doing that for our simple two-state system, we obtain a 2D single Lorentzian peak. Now, to add a little bit more complexity to our system, due to spin-orbit coupling, each of our ground state and excited state was split into 2 states each, giving us a total of 4 states. This results in 16 Lorentzian peaks, which stem from the 16 combinations of each pair of our 4 states. Delta ZPL determines the overall center frequency of our 16 peaks. Delta ES determines the separation between each set of 4 Lorentzians, and delta ES determines the separation between 2 individual Lorentzian peaks. Based on experimental data, we know that not all Lorentzian peaks have the same amplitude. For easier interpretation, we can project our 2D spectrum onto the horizontal axes. Now that we have our unstrained 4-state system, we can go ahead and start incorporating the effects of strain. Employing group theory, Misala et al. Writes down the Hamiltonian for the strain and derives the delta ZPL in terms of the strain components. By varying the strain, we can perturb the delta ZPL splitting. They also derive delta GS and ES in terms of the strain components, and likewise, by varying the strain, we can vary each of these 2 splittings. Now, this leads to the result where our density matrix element would now be a function of the strain components. A natural question that arises is, how does strain vary in our diamond sample? Well, when in doubt, first try a Gaussian, and that is exactly what we did. We then integrate over all 6 of the strain components, weighing it with a normal distribution. And a physical interpretation of this is that a bunch of SIV centers are unstrained, and a bunch of others are strained according to the normal distribution. Well, the most efficient way to solve a 6D integral that I know of is via a Monte Carlo integration. And by doing so, we obtain the following 2D spectrum. For easier comparison, we can again project onto the horizontal axes. And here we see the raw simulation data to be rather noisy. And that is because I can only use a finite number of random numbers in my Monte Carlo integration. We can then compare the full width at half max of the 2 spectrums. And going back to the Gaussian that I had, I can vary the standard deviation of this strain Gaussian such that we match the 2 full width of half max. And this would entail a standard deviation of the Gaussian, of the strain Gaussian, of 2.75 times 10 to the minus 4. Now, I can split my Gaussian into a product of 2 Gaussians with 2 different standard deviations, one for the axial, one for the shear strain. This allows me to manipulate the shape of my spectrum to better fit my experimental data, namely more of a concave up profile on the right, a concave down profile on the left. And this entails a standard deviation of the axial strain Gaussian of 4 times 10 to the minus 4, and for the shear, 10 to the minus 4. In addition to varying all 6 strain components with a normal distribution, we also develop a few other strain models. But at the end of the day, it is our initial model that produces the best result. Now, so much for the heterodyne detection. What about the photoluminescence detection? As some next steps, I'm currently trying to incorporate an additional dark state to each pair of 2 states, with the hopes of creating a filtering mechanism that will filter out the strict SIV centers that are only visible in heterodyne, but are hidden in photoluminescence. And with that, I look forward to your questions.